All right, so we're going to talk about energy and chemical changes, specifically thermal chemistry. So we're first starting with heat flow. So heat flow, so which way does heat naturally flow? So if you can imagine, like if you have a hand, and that hand is holding ice, that ice will melt. Why? Because the heat from the hand will go to the ice, so that's known as heat flow. So the hand is hotter, so it has more heat. The ice has less heat, so heat goes from high to low. So the hand feels colder. Why? Because there's less heat. The heat's now moving from the hand to the ice. So what would you feel? You would feel, if heat is leaving you, you would feel cold. If heat's coming towards you, you'll feel warm. What are the two ways heat flows in chemical reactions? Well, it can either be exothermic. And so exothermic is when heat is produced, so it flows out. And so, since it's produced, we put heat on the product side. And then endothermic, where heat flows in. So this is where heat goes in, and so that's on the reactant side. All right. So endothermic reactions is when energy is absorbed during the reaction. So if we have a reaction in an Erlenmeyer flask, here's the reaction. If this is an endothermic reaction, the heat will flow in, so therefore it would feel cold if your hands were on the outside. So let's say your hands were out here, and the heat is flowing away, your hand would feel cold. So oftentimes endothermic reactions we feel as cold, why the heat is leaving and going into the reaction. Exothermic is the opposite, where energy is released during the reaction. So imagine you have your Erlenmeyer flask with a reaction. So here's your reaction. Heat is flowing out. So if you have your hand out here, you'll feel heat, right? You'll feel the heat. And so exothermic reactions we feel as hot. So here are examples. So is this exo or endothermic? Well, what you'll notice is that there's heat on the product side, which means it's an exothermic reaction. That heat is produced. So during a chemical reaction, the breaking of bonds is an endothermic process, where the formation of bonds is exothermic. One way to think about it is when atoms are separate, they're at a high energy level. And the reason why they bond is so that they can get to a lower energy or become more stable. And so here they're bonded. So this is at a higher energy, and this is at a lower energy. So what I want to show you was that at lower energy, if they bond, they go from a high to a low, which means there's this excess. So let's say, let's just give it a number. This was 10, and this was 5. There's an extra 5 that are remaining, right? And so that is given off. So you have energy that is given off. But if we reverse the process, going from 5 to 10 or from low to high, you have to add energy. So you have to add energy. So anytime you add energy, that's endothermic, sorry. And anytime energy is given off, that's exothermic. Okay. To start a reaction, you need what's called activation energy. So that's energy to start a reaction. All reactions require activation energy. Examples would be heat, friction, light, and electricity. So here we have an energy graph. So of energy on the y-axis and time on the x. So we always start a reaction with a reactant. And then to start a reaction, we always need activation energy. So this will be the activation energy. This is the amount of energy required to start a reaction, right? Remember, a reaction always starts with reactants and then goes to the products. So this is the activation energy. And then eventually you'll get to the products. So we want to determine, is this an exothermic or an endothermic reaction? And what you notice is that the products, so let me remove the activation energy. So the energy put in is from here to here, right? So this is the amount of energy put in. The amount of energy that we got out was between here and here, right? Kind of like a roller coaster. Like you put this amount in, oops, you got this amount out, and you got this amount in. So what you'll notice is that the amount of energy taken out is greater, right? The amount of this, so this is the energy produced. This is the energy put in. And so there's a difference between the two. So between here and here, there's a difference, right? And so I guess I can make that a little lower, so like from here. So there's more energy produced. Well, when you have more energy produced, that's going to be exothermic. So this is an example of an exothermic reaction, why there's more energy produced than energy put in. So if we draw an endothermic reaction, it'll look like this. So here's your reactants. So this is your activation energy, or the amount of energy you put in, right? So in an endothermic reaction, we need to put more energy in than we take than is produced. So the product has to be like here. I mean, it could be somewhere along here, as long as the energy that is produced is less than the energy that is reacted. So this is an example of endothermic. And lastly, so does this represent an endothermic or exothermic reaction? Well, this is a exothermic reaction. Why? Because the amount of energy produced is more than the amount of energy put in. Okay. And lastly, we can speed up reactions using catalysts. So sometimes catalysts within biology are called enzymes. And what catalysts do is, you can see here on this chart, so normally so from here to here, this is your activation energy, right? But this is without a catalyst. With a catalyst, notice how small the activation energy is, or how low. So the big catalysts speed up reactions by lowering the activation energy. So let's highlight the words that make the statements correct. So in an endothermic reaction, endo means the heat is going in, so it's required. Since the heat is going into the reaction, the vessel itself will feel cold. Why? Because heat is leaving it. Activation energy is the minimum amount of energy required to start a chemical reaction. And an enzyme, which is the biological term for catalyst, speeds up a reaction by lowering the activation energy. Sorry, that's in the way, but it says lowering the activation energy.